In this lecture, we're going to cover two of probably the most important concepts in statistics for the semester. And those concepts are the concept of probability, which we've kind of touched on a bit already, and null hypothesis statistical testing, which is the general framework for all of the different statistical tests that we're going to use this semester. So one thing, when I start talking about probability, I always like to start with this quote from this book called Against the Gods, which is, as nerdy as it is, it's a book about statistics, and I think it's a really interesting read. So this quote says, "The revolutionary idea that defines the boundary between modern times and the past is the mastery of risk, the notion that the future is more than a whim of the gods and that men and women are not passive before nature. Until human beings discovered a way across that boundary, the future was a mirror of the past, or the murky domain of oracles and soothsayers who held a monopoly over knowledge of anticipated events." So what this means, what I think is so important about this quote and why I start my lesson on probability with it, is that it tells us that there's this time in the not-so-distant past where people realized that there was a way to quantify or put a number on how likely it was for things in the future to happen. Before that time, before that discovery, people did not have a sense of control over future events, or didn't even have a way to kind of envision what the future was going to be like. People assumed that whatever was going to happen was totally and completely up to chance, and that this is not something that they could plan for or do anything about, that the future was just bound to happen and they had to adjust to it. Once we crossed that boundary, once we got to a point in time where the future was not completely uncertain, where we actually knew with a certain degree of confidence what was going to happen in the future, what events were more likely and what events were less likely, it opened this whole new world of planning for the future and actually even investing in the future that created new economies and new businesses. And it really is this bridge from kind of the past and modern times. So I know that sounds dramatic, but in reality, this understanding of what probability is a really, really powerful and important thing. So I want to make sure that you all understand it because it's so pervasive in our lives today. It's really what makes our society the way it is today, modern and predictable, and something that we can plan for, where throughout most of human history that wasn't the case. So let's talk about what probability is at a very basic level. So probability is this study of likelihood and uncertainty. It's the difference between knowing something will definitely happen and knowing something that there's no chance it will happen, and then all that in-between area where you can't say that it's definitely going to happen and you can't say that it's definitely not going to happen. Everything in between that is probability. There's a certain chance that it will happen, and how do we put a number on how likely that chance is? If we want to get mathematical about it, probability is the total number of ways that some particular event or outcome can occur divided by all of the different possible outcomes. So we're interested in one specific outcome out of a whole range of possible outcomes, and so we take the number of ways that one outcome can occur divided by all the possible outcomes, and that gives us the probability. So the formula for that would be probability, represented by P, equals a specific event over all possible events that could occur. Right? So if you think about it, a lot of our daily life depends on probability and assumes some knowledge of probability. Things like weather forecasts tell us the probability that's going to rain or snow. That's been pretty important lately, right? The whole industry of insurance, car insurance, health insurance, life insurance, renter's insurance, homeowner's insurance, that whole industry is based on being able to forecast the probability that something bad will happen. Car insurance, for example. If you have car insurance, your car insurance premium, the amount you pay, is based on the likelihood that the car insurance company thinks that something will happen to your car, whether that's an accident or getting broken into or something just going wrong, that they'll eventually have to cover with your insurance policy, right? So the insurance company wants to be profitable, so they're going to do everything they can to calculate the probability that they're going to have to pay you money for your insurance claims, and they're going to charge you enough of an insurance premium on a monthly basis so that even if they have to pay the likely claims that they think they're going to have to pay to you over the course of the time you own that policy, that they're still going to make more money from your payments than they're going to have to pay back out to you, right? That's their whole business plan. If they don't do that well, they don't make money, right? So they put all of their time and effort into being able to forecast the probability of having to pay an insurance claim based on whatever characteristics they can use, right? Medical advice is another one. It's really important to understand probability. If you go in and talk to your doctor and they say, well, maybe you have this medical condition, or you have this condition and here are the possible treatments and here's the risks associated with those treatments. If you don't understand and have a good intuitive sense of what the probabilities and risks associated with those treatments mean, it's really hard to make decisions for yourself based on that information, right? So what I'm trying to do here is give you a lot of reasons for why you should care about probability and why it's important, no matter what you do after you get out of school, to understand probability and what it tells you. So let's start with some examples. Easiest example is an example of flipping coins, right? So if you're going to flip one coin, the probability of flipping heads is 0.5, right? Or 50%, 50-50. So essentially, if you want to, we'll consider the math that goes along with this. A coin has two sides. If you flip a coin, there's one way you can get heads. It can land on heads. There's two possible outcomes. It can be heads or tails, right? So that one outcome that you care about, divided by the two total possible outcomes, gives you the probability of 0.5, right? It seems like a very simple example, but it's good to use that simple example so that you can, at a very basic level, start to understand how we put a number on the probabilities associated with different events. So the next thing we want to talk about then is independent outcomes, and we'll continue with the coin flipping example. So if you know that the probability of flipping a coin that comes up heads is 0.5 or 50%, what happens if we flip two coins? So if we flip a coin and it comes up heads and we decide to flip it a second time, right? So we already got heads once. What's the chances, or what's the probability that it's going to come up heads again that second time, right? Or if we flip heads 9 times in a row, what are the chances that it'll come up heads again on the 10th flip? So I put these examples up there because I want to challenge your intuition, right? In both of these examples, the probability is still 0.5 or 50%, because once that first coin comes up heads, the probability that the second coin comes up heads is still 50-50, because that outcome is independent of the flip before it. Even if you flip 9 heads in a row, right, which is rare, but once you do that, the probability of that coin coming up again heads on that 10th flip is still 50-50, right? So we get this intuitive sense, especially in this second example. If you were to flip 9 heads 9 times, we think, oh man, I'm due for a tails, right? But we're not due. Those first 9 flips of the coin have absolutely no bearing. They do not influence that 10th flip at all. So there's a difference. What I'm trying to show here is there's a difference between the fact that flipping heads 10 times in a row definitely is a rare event. But once you've flipped 9 heads, flipping that 10th coin heads again just has a probability of 50-50, right? So those are two very different probabilities. And if we're only concerned with the probability of the flip itself, of that second flip or that 10th flip, then that probability is still 0.5 every single time you flip the coin. There's only two possible outcomes, heads or tails, and heads is the one that you care about. and that's the only thing that matters, no matter what has happened before that, right? So just to underscore, the probability of that coin coming up heads is 0.5 every single time, no matter what has happened before you flip the coin, right? And so the way we would state that in a discussion of probability, we would say that each coin flip is independent. That means the probability of it coming up heads on any given flip has nothing to do with what happened on any other coin flip. And it's important to know when when outcomes are independent from one another, right? Because we do get, and this is a psychological phenomenon, we do get this intuitive sense that once we flip the coin heads 9 times in a row, that's so rare, there's no way it's going to come up heads a 10th time. But we have to remember, we have to push that intuitive sense out and say, you know what, the flip of this 10th coin is still 50-50. It doesn't matter what happened before. The only thing that's rare is that whole set of outcomes, or getting 10 in a row as a whole is very rare, but each independent flip has a 50-50 probability or a 0.5 probability each time. Right? And so let's talk about that more complicated sense where we want to know the probability of getting multiple flips in a row, right? So if we know that coin tosses are independent and we know that the probability of the coin coming up heads is 0.5, what if we do want to know the probability of flipping 2 heads if we know that we're going to flip a coin twice? Right? So we can do the math again. We can actually figure this out 2 ways. We can say, what are all the possible outcomes of those 2 flips of the coin? So there are 4 possible outcomes. 2 heads, heads tails, tails heads, or heads heads. Right? So there's 4 possible outcomes. There's only one way to get that outcome that we're interested in, the heads heads. It's only one of those 4 possible outcomes, and there's only one way that comes up. So the probability, given our basic formula for probability, is 1 divided by 4, or 0.25. So we have a 1 out of 4 chance that we get 2 heads if we flip 2 coins, right? There's 3 other things that we could possibly get. The other way we can get to the same answer is we can multiply the probability of each independent outcome, right? So each of those independent flips have a probability of 0.5, and if we multiply the first flip with a probability of 0.5 times the second flip with a probability of 0.5, it will give us the same answer, a probability of 0.25 of getting that same outcome on both flips of the coin. Okay, so let's carry this example a little bit further. Let's go with 3 coins. What are the chances of getting all heads with 3 coins? Well, again, we can do this one of 2 ways. We can map out all the possible outcomes. So we can have all tails, we can get 2 tails and a head, tails, heads, tails. And keep in mind here, when I put all these outcomes, I'm talking about the order with each independent flip, right? So you'll see that there's multiple ways we can get 2 tails and a heads, or 2 heads and a tail, and that's fine. But I still have to list all the possible orders, right? Because that's all of the different sequences of 3 flips that I could possibly have. And there's 8 different sequences there. 3 heads is only possible one way, right? You can only get heads each of the 3 times. There's 7 other different sequences that could come out of flipping 3 coins, one after another, right? So again, we have a 1 in 8 probability, 0.125. We can also, if we want to calculate that probability, we can also just multiply 0.5 times 0.5 times 0.5, and it'll give us that same answer of 0.125. We could ask the question a little differently. We could say, what are the chances of the coin coming up on the same side 3 times in a row, right? So that's a little different question. We don't care just about heads now. We're just saying, what are the chances that we flip the coin 3 times and it comes up on the same side all 3 of those times? Well, now we're adding another potential outcome to the numerator of our equation, right? So we've turned this into 2 out of the 8 possibilities are ways that we could get that outcome of 3 on the same side, right? So 2 and 8 would be 0.25, right? what if we change the game a little bit? What if we start going with dice, right? So this is just another way to use our knowledge of what a probability is to figure out and get a comfort level with how we are going to quantify or put a number on the probabilities of certain events. Right? So let's say we have 2 dice and we want to know what the probability of rolling boxcars is. Boxcars is 12. They call it boxcars because if you put those 2 dice back to back, it looks like 2 train cars, maybe. I don't know, if you use your imagination. Right? But so we want to know what the probability is of rolling a 12 with a pair of fair dice. All right, so we have 2 dice, and each individual dice can produce, or die can produce one of 6 possible outcomes: 1, 2, 3, 4, 5, or 6. Right? So if we want to know all possible combinations of those dice, of those 2 dice, right, and all possible combinations, even though we could have a 1 and a 6, we can have that 2 different ways, right? We can get a 1 with the first die and a 6 with the second die, or we can get a 6 with the first die and a 1 with the second die, right? So we have to think of all those possible outcomes. So you can figure that out by saying, well, each die has 6 outcomes, so there's 6 possible pairings for each of the 6 pairings of each die, or another way to say that is we can multiply 6 times 6, and we get 36 possible combinations of the 2 die. So that's the denominator of our probability equation. There's 36 possible outcomes. How many outcomes will give us 12? Only 1. You have to get 6 on both die. So 1 out of 36 is the only way to get a boxcar, right? So it would be 1 divided by 36, which is about 0.03, about 3%, right? So 3 times out of 100 would be another way of saying that. You can expect to get 2 6s when you roll a fair pair of dice. Right? The other 97 out of 100 times, you should expect to get something else. Differently, we could ask, what's the probability of rolling a 7? Well, if we know that there's still only 36 possible outcomes, but there's a lot of different ways to get 7. Our first die could be a 1, our second die could be a 6, our first die could be a 2, our second die could be a 5, 3 and 4, 4 and 3, 5 and 2, 6 and 1, right? So there's actually 7 different ways, or I'm sorry, there's 6 different ways to roll a 7 with the 2 dice. And so 6 out of 36, that's equivalent to 1 out of 6, or about a 0.17 probability of rolling a 7. Any combination that gives you a 7, you have about a 17% chance, or the probability of 0.17. Right? So that's a lot higher probability of rolling a 7 than rolling a 12, because there's a lot more ways to actually get a 7 out of the combination of 2 fair. So let's focus now on a different example using cards. Right? So if you pick 1 card from a regular fair deck of cards, no jokers, just the regular 52 cards that you would have in a deck, what's the probability that you'll pick the Queen of Hearts? There's only 1 Queen of Hearts out of those 52 cards, so that's a 1 out of 52, or 0.02 probability of picking the Queen of Hearts on 1 pick. What about the probability of picking any queen? So there's 4 total queens in the deck, right? So 4 out of 52 is the same as 1 out of 13, which is about an 8% chance. I apologize, this slide should say 0.08, not 0 divided by 0.08. That should be 0.08. Okay, so we've talked now about a lot of different ways to calculate basic probabilities. We take the number of events and divide it by the number of possible outcomes. Then we have this other, a little bit more complicated problem that comes up, and it's called the problem of multiple comparisons. So it's easy to figure out the probability of getting all heads if we flip, let's say, 2 coins. It would be 0.5 times 0.5, which is 0.5 squared. So there's a 0.25 probability of getting all heads with 2 coins. Even if we do 4 coins, 0.5 to the 4th power, or that's 0.5 times 0.5 times 0.5 times 0.5. We can calculate that probability pretty easily. It's about 0.06. Even if we did 10 coins, right, the math is maybe a little more repetitive, but it's no more difficult to just put that into your calculator and calculate the probability. The probability gets very small, right? If we flip 10 coins, the probability of getting all heads is about 0.0009, about 0.001. Right, but a pretty slim probability. But let's ask the question a different way. What if you had more than one chance of flipping 2 coins, or flipping 4 coins, or even flipping 10 coins? What if I said you can flip 10 coins, and I want to know what the probability is that you get all heads at least once, right? Let's actually use the 4 coin example because the math is a little bit easier to work with. So if I said, what's the probability of getting 4 coins to come up all heads at least one time if I give you 4 separate chances to flip all 4 of those coins, right? So what I'm saying is you can flip 4 coins once, and if you don't get all heads, you can flip them, all 4 of them again. And if you don't get all heads, you can flip all 4 of them again. And if you don't get all heads, then you can even flip them one more time, all 4 of them. And I want to know if you do that, if you flip 4 coins 4 separate times, what's the chances that at least one of those times you'll get all 4 heads, right? So there's a formula that we can use to calculate that probability. And this is general. It's the probability of any event happening at least once if we give it multiple opportunities to occur, right? So the formula looks like this. It looks a little scary. 1 minus p to the nth power, right? Don't get freaked out by the math formula there. It actually makes a lot of sense, right? So remember that p stands for probability. So the inside of the first parentheses there, 1 minus p is just the probability of something not happening, right? So if I say the probability of something happening is 0.2, right? The probability then of it not happening is 1 minus 0.2 or 0.8, right? So 1 minus p is just the probability of something not happening when you know the probability of it happening, okay? So let's start there. So that's really just another probability, right? We label it 1 minus p, but the probability of something not happening is just the probability of something happening, right? It's just a different event. So if we know the probability of something happening, the probability of something not happening is just a different probability. And so when we raise that to a power, the nth power, that n just stands for the number of chances we give that thing from happening, or the number of chances we give that event to happen, right? So that's no different from in the top of the slide when we say the probability of flipping 4 coins all heads, we take the probability of 0.5 and raise it to the 4th power, right? We're really doing the same thing down here. It's just that we're taking the probability of something not happening and raising it to a power, right? So if in my example I was going to give you 4 coins and the chances that it was going to come up all heads at least once, right? I'm just raising that. I take that probability that I got in that 4 coins example up there, and I subtract it from 1, and then I raise it to the 4th power, and I'm really doing the same thing that I did up there when I take that probability and say, okay, well, I'm going to give it 4 chances to happen, so I'm basically going to multiply it by itself 4 times, right? It's just that instead of the probability of it happening, that'll give you the probability of it not happening on those 4 times, right? And then we finish that up by subtracting it from 1 again. So what we're really saying is it's the probability, we take the probability of a thing not happening all 4 times, and so 1 minus that probability is the probability that it happens at least once out of those 4 times, right? And so if I want to do the math there, you'll see that I just plug in the values. The 0.0625 comes from my 4 coins example up top. And the 4 that I substitute in for the n just means that I'm giving that 4 heads probability, 4 chances to happen, right? And when I do the math, that gives it an overall probability of happening of 0.23 or 23% of the time, which means, and that should be intuitive, right? If we flip 4 coins and we want to know the probability of them all coming up heads, that probability is 0.0625, right? So that's the probability of it happening that time. If we give it more chances to happen, it should be more likely that it eventually at some point will happen, right? So the more opportunities we give it, the higher that probability should get, right? And that is what happens. We have a higher probability. The overall probability that happens at least once is 0.23, right? The takeaway from that is, what I want you to understand about this, in addition to knowing how to calculate that actual probability, is that if we give something enough independent chances to happen, even if it's extremely rare, eventually it's going to happen. The probability that it happens at least once will eventually get very, very high, right? And the more chances we give something to happen, even if it's a very rare thing, the more likely it is that it'll eventually happen at least once, right? And so we can apply this to things in our life that seem extremely rare, right? If you talk about the probability of getting dealt a royal flush in poker is very, very rare. A royal flush, if you don't know, is if you get the 10, Jack, Queen, King, and Ace, all of the same suit dealt to you, right? So that's a very specific combination of cards, and it's very rare that that happens. But if you get dealt hundreds or even thousands of hands of cards, the probability that you'll eventually get that at least once starts to get pretty likely. You can also apply this to watching a perfect game in baseball or winning the lottery, right? And so it's really interesting. This kind of underlies a lot of our superstitions, right? We think that we get really lucky or we do something that creates luck, right? But we forget that even things that are really rare, if we give them enough time or enough opportunities to occur, it's pretty likely that it's going to happen at least once, right? So just keep in mind what this tells you. If you understand probability, you understand that increasing the number of chances for some event to occur is going to really, really quickly increase the probability that it actually does occur at least once. And so apply this to doing something like betting on your lucky number, right? If you bet on your lucky number every day, and for years and years and years, you don't win, and then eventually it comes up, that's not really much of a lucky number, right? But we think of it as a lucky number because, wow, I played that number and, it came up, right? It actually happened, so it must be lucky. Well, no, it's just that you gave it enough times or enough opportunities to happen, so eventually it would be actually really rare if it didn't happen, right? If it didn't come up. This is a really important concept for statistics because, and we'll get to this in a second, but every time we test a hypothesis, there's going to be some probability that the results that we get lead us to an incorrect conclusion about that hypothesis. And what that means is the more hypotheses we test, the better and better the chances that at least one of the hypotheses or one of the conclusions that we drew from our statistics represents an incorrect conclusion, right? Because basically we get a probability. That's the results of our statistical tests are always a probability that we draw a conclusion from, and you'll see more of that in a second. But the more statistical tests that we conduct, the more likely it is that we will make an incorrect conclusion based on those probabilities. All right, so just keep that in mind, and you'll see what we mean as we go. So we already talked a little bit leading up to the first exam about the standard and normal distribution, and we talked about probabilities in this distribution. Remember that this distribution is helpful for estimating the probability of observing some value in a given range, right, based on knowing a z-score in a normal distribution. If we know what value is associated with a certain z-score, then we can calculate the probability of observing a value greater than or less than that z-score, or between the mean of that z-score. So we've already worked with probabilities to a certain extent, right? And so keep that in mind, that our knowledge of probabilities and now understanding what that numerical probability means and thinking about it in the context of this normal distribution is really going to be the basis for all of the statistical tests that we're going to conduct. And it's going to, hopefully, over time, you should develop a good sense of why the probabilities we're conducting or why the tests we're conducting make sense if you understand the probabilities behind them. All right, so we're about halfway through, so just to recap things to remember so far. One is understanding probability is not just crucial, it's essential for understanding inferential statistics. And inferential statistics, or sometimes you'll hear them called null hypothesis statistical tests, are what we're learning in this course. All of the statistical tests that we conduct are going to be inferential statistics. And inferential statistics means that we conduct a test based on a sample of data, and we infer something about the population that sample came from. That's what inferential statistics means. When we do that, we can only calculate the probability that we know something about the population. We can never be 100% certain, right? So because of that, we really need to be familiar with what our probabilities are telling us. Understanding probability relies on this understanding of the relationship between one outcome and all possible outcomes, right? So that's what probability is, the likelihood of one event to occur out of all of the possible outcomes that could occur. We got to understand, we got to keep in mind as we go that if we don't make adjustments for this multiple comparisons problem, we can underestimate the probability of an event. We can conclude that a certain event was really rare and unlikely when, in effect, if we gave it a lot of chances to happen, it would actually be surprising if it didn't happen at least once. So we've got to keep that in mind as we go. And the last thing we talked about there was if we combine our understanding of probability with that standard normal curve, it allows us to make some educated estimates about the likelihood of the things that we observe when we gather data and conduct statistical tests. Okay? I understand that there's a lot more to do, but make sure that you're good on at least those 4 points before you go further with this video lecture. Okay. So now that we've covered basic probability, I want to talk about how we make and test hypotheses with statistics. So first, let's talk about what a hypothesis is. We could formally define hypotheses as tentative statements subject to empirical tests about the expected relationship between variables. And that is what they are, right? All of the tests, all of the hypotheses that we're going to test and all the statistical tests that we're going to conduct this semester are going to test some prediction about a relationship that we expect to find between variables. Okay? That's kind of a mouthful. We could say there are propositions that flow logically from a theory. Okay? It's one other way to say it. But if we want to just talk about what a hypothesis is in plain language, it's a prediction, right? We are making a bet, essentially, that something is true. It's not a guess. We don't just assume. It's not a guess. We don't just kind of pull our hypotheses out of thin air. We're making a prediction based on some knowledge that we've acquired up to the point of making the hypothesis. We're betting that a certain relationship is going to exist between variables, and then we want to test the probability of that relationship, right? So that is what a hypothesis is. It is a prediction, not a guess. So some examples of hypotheses that we might come across in psychological research or just human behavioral research, right? We could hypothesize or predict that increases in anxiety will be associated with decreased social interaction, right? So I'm making a specific prediction about the relationship between anxiety and social interaction. And my prediction is that when anxiety goes up, social interaction will go down, right? That's a specific prediction about what the relationship between those variables is going to be like. Another example would be the closer somebody is to the front of a roller coaster line, the more frustrated they'll become if somebody cuts in front of them. Okay? So I'm talking about, again, the relationship between two variables. The first variable is the distance between somebody in the front of the roller coaster line, and the second variable is the level of frustration of the person that gets cut in front of. Okay? So these are two things that we can measure. They're two things that we can quantify. So we've got two variables there, and we're making a prediction about the relationship between them, specifically that if the distance between somebody in the front of the line is shorter, that when somebody cuts in front of that person, they are going to become more frustrated. Final example of a hypothesis, children older than 12 months old will demonstrate better object permanency compared to children younger than 12 months old. Object permanency is the awareness that when an object disappears, when it's out of sight, it actually still exists. Right? So this is a phenomenon that's studied often in developmental psychology. So this is a different kind of hypothesis, but it's still a relationship between two variables. It's actually a relationship between a nominal variable and a continuous variable. So my nominal variable is the age of the child, and I've basically given two categories for that age: children older than 12 months and children younger than 12 months. So that's one variable, the age of the child. And I'm predicting with this hypothesis that age of the child variable is going to be related to their ability or their knowledge of object permanency, right? So that could be a variable that's quantifiable, where higher scores mean better object permanency, right? And I'm assuming, or I'm predicting, that children who are categorized as being older than 12 months will have better object permanency than children who are categorized as being younger than 12 months. So that's a relationship between the age variable and the object permanency variable. So again, a predicted relationship between two variables. This is one thing that I'm going to make sure that I drill into your heads throughout the semester, that when we're talking about testing hypotheses with statistics, especially with inferential statistics, there is no way that statistics can prove anything. The only way you can prove anything is through math. You cannot prove things with statistics through experimental research, right? Theories and hypotheses can be supported, or they cannot be supported by the result of a research study. But we can never prove them, because all the statistics that are involved in research can ever give us is the probability of some hypothesis being true or not true, right? But we can never have a 100% probability of anything, right? We can be very, very sure. We can have a lot of support, but we can never have absolute proof. It is impossible to prove things with research and with statistics, so keep that in mind. We can be very confident in things. We can develop a high degree of confidence, or we can show that a relationship is probably not true, but we can never prove it. Right? So the question is, how do we determine whether or not our hypotheses are supported? And the answer to that is through inferential statistics, the types of tests that we're going to use this semester. So what are inferential statistics? Right? This is what we use to test research hypotheses. Inferential statistics are actually a formula or a system of testing predictions based on two concurrent hypotheses. We call them concurrent because we make two hypotheses at the same time. We have a null hypothesis and we have an alternative hypothesis. And in general, what the difference between these two hypotheses are that the null hypothesis is that whatever that relationship that we think is there between our variables, the null hypothesis is that that relationship does not exist. The alternative hypothesis is that the relationship does exist. So all those examples of hypotheses that I gave in the previous slide, those would be alternative hypotheses. The null hypothesis is that those relationships between the variables, those predicted relationships, don't exist. These sets of hypotheses, and we always deal with them in sets, can be either directional or non-directional. Directional means that we predict a specific numerical relationship between our variables. So if we predict that when one variable increases, the other variable will also increase, that's a directional hypothesis. If we predict that one variable will be related to another variable, but we don't make a specific prediction about whether an increase goes with another increase or an increase goes with a decrease, that would be a non-directional hypothesis, right? And we can do both, and we're going to talk about directional and non-directional hypotheses for every type of statistical test we do. But at this point, what I want you to understand is a null hypothesis is that the relationship between the variables does not exist, and the alternative hypothesis is that it does exist. We always start by assuming that the null hypothesis is true. we always assume that there is no relationship between our variables. And until we have enough evidence to show that that's probably not the case, we stick with that, right? So this is a key point. If you learn this and you understand what this means, this is going to help you out a lot for the rest of the semester. The results of any test of inferential statistics that we conduct this semester, the results will always tell us what the probability is that the null hypothesis is true, right? Let that sink in. Any statistical test we do, what it tells us is the probability that the null hypothesis is true. This will give us the test will actually give us the probability. This value, we call it the p-value a lot. It stands for the probability, right? The p is for probability. But remember, drill this into your head. That p-value is the probability that the null hypothesis is true. We generally, when we're conducting research, we don't want our null hypothesis to be true. Our predictions are the alternative hypothesis. So when we get these probabilities from our statistical tests, what we hope to find in most cases is that the p-value will be really, really small. If we have a very low probability that our null hypothesis is true, that's evidence then to support that the alternative hypothesis is probably more likely to be true than the null hypothesis. And that's how we draw some conclusions with statistics, right? Think of it this way. Think of this relationship with testing the null hypothesis in terms of the prison system, or how the prison system is supposed to work, in terms of whether somebody is guilty or not guilty. Think of that as the null hypothesis being whoever the suspect is. The null hypothesis is that they're not guilty. We're supposed to always start by assuming that the person is not guilty. The alternative hypothesis is that they're guilty. We assume, or we're supposed to assume, that somebody is innocent until there's overwhelming evidence that the suspect is guilty, right? But we start with that null hypothesis that they're not guilty until we have enough evidence that we can reject that in favor of the alternative that they're guilty, right? It's the same way with statistics. So if you think about it, the prosecuting attorney, the person who is responsible for trying to convict the person that's on trial, hopes to reject the null hypothesis. They think that the subject is guilty, right? But they are not going out there. They're starting with the assumption that the subject is not guilty, and they're trying to find enough evidence to overturn that assumption of innocence, right? Along with that, we got to point out that we don't ever accept the null hypothesis. When the prosecuting attorney is putting somebody on trial and trying to convict them of a crime, they are not collecting evidence of innocence, right? So we may conclude the null hypothesis, but we are not making that conclusion based on the fact that we've gone out and collected evidence that somebody is innocent, right? We start by assuming somebody is innocent, and all of the evidence is supposed to show that they're not innocent, right? So if we make that conclusion, if we fail to convict somebody, if we fail to show that somebody's guilty, it's not because we proved they're innocent. We started with the assumption that they were innocent from the first place. We just didn't get enough evidence to overturn that innocent assumption and convict them and assume that they're guilty, right? So the same thing is true when we conduct statistical tests. We start by assuming there's no relationship between our variables, and if we get enough evidence that shows that there is a relationship, we will reject the null hypothesis in favor of the alternative. But we don't ever go out and try to find evidence that there is no relationship. We're always looking for evidence of a relationship, right? So another way to think about this in our example is a person is found innocent. They're not proven innocent. They're found innocent if there's a lack of evidence for guilt, right? We fail to reject the null hypothesis if we don't have enough evidence to overturn it, right? But we don't go out and collect evidence for the null hypothesis. We're going out and collecting evidence for the alternative hypothesis, right? So when we conduct statistical tests, our decisions are based on whether or not we decide to reject the null hypothesis. So we need to have some criteria for when we're going to do that. When are we going to reject the null hypothesis? We call this criteria the alpha level, and we'll represent it with alpha. The alpha is a number, and the number represents the maximum probability of the null hypothesis being true that we're okay with for still rejecting the null hypothesis. So as a researcher, we decide what we want our alpha level to be. We set it. This is not something that's part of our data. This is just something that we decide what it's going to be as a researcher. That's up to me as a researcher. What do I want my alpha level to be? And so I will decide, and what I'm deciding is what is the probability where I'm going to say, okay, that is a low enough probability that if the probability of my null hypothesis is true is lower than that, then I'm going to reject the null hypothesis. All right? So in essence, the alpha level conveys the amount of risk that we're willing to take that we end up rejecting the null hypothesis when really it's true. Right? And so if we do this, if we reject the null hypothesis and we conclude that our alternative hypothesis is true, we've made what we call a type 1 error. Right? A type 1 error is rejecting the null hypothesis when we shouldn't have, when we should have failed to reject it. If we reject a null hypothesis, we call that support for the alternative hypothesis. So if our statistical test tells us that the probability that our null hypothesis is true is really low, it's actually lower than our alpha value, then we'll reject the null hypothesis and we'll call that support for the alternative hypothesis. Keep the alpha value in perspective. It is not magic. In psychological research, most research studies use an alpha value of 0.05, meaning that if they run their statistical test and the test tells them that the probability of their null hypothesis is true is 0.02, right? If it's less than 0.05, then people will conclude that that's sufficiently low. There's a very low chance that the null hypothesis is true. We're going to reject the null hypothesis in favor of the alternative hypothesis. Okay, that's the decision process and how it would occur. Most people use this value of 0.05 in psychological research, and we're going to use that throughout the semester. But remember that there's nothing that makes 0.05 the correct criteria to use. Honestly, what probably happened is when people were sitting around, maybe drinking a couple beers, they said, what do you think we should use as the alpha value for our statistical test? And they said, well, 0.05 sounds like a good enough value. Let's use that. And that's just the way it went. There's no other reason why that would be the right value. It's just the value that gets used most often. But keep in mind, what does that alpha level of 0.05 mean? It just means that this is the point where you're drawing a line in the sand and you're saying if the probability that the null hypothesis is true is lower than this value, I'm going to reject the null hypothesis. If it's greater than this value, I'm going to fail to reject the null hypothesis. We have to have some value, and this is the value that it just ends up being. But there's nothing that makes 0.05 magically a magically different probability from 0.06 or 0.04, right? So it's not like all of a sudden when we cross this boundary point that we suddenly have a relationship between our two variables that didn't exist when we were just had a little bit higher probability of the null hypothesis being true. That would be silly, right? But we have to have some value, some line in the sand where we're going to change our decision, and this is just what it happens to be most of the time. But don't get caught up into thinking that that value means something special, right? It's just the point where we decide to start making that decision. Okay? The next concept that we want to talk about is statistical power. So statistical power is the likelihood of rejecting the null hypothesis when it's false, right? And we want to reject the null hypothesis when it's false, right? That's a good, correct decision. So the power is the chance or the likelihood, the probability that we're going to do that in a test. Unfortunately, unlike the alpha value, we don't have control over statistical. Well, we kind of have control over it, but we can't just decide what it is, right? With the alpha value, we just decide what our alpha value is, and that's our criteria for when we're going to reject the null hypothesis. We don't make that same type of decision with statistical power. The reason for this is because the probability of us rejecting the null hypothesis when we should depends on a couple of different things. It depends on our sample size. So higher sample sizes will give us higher statistical power. Lower sample sizes will give us lower power. So when we have a bigger sample size, there's a better chance that we're going to reject the null hypothesis when it's false. With a small sample size, we have a much lower probability of our statistics telling us to reject the null hypothesis when it's false. Effect size is the second thing that matters. Effect size is the real relationship, the magnitude of the real relationship that exists between the variables, right? So sometimes variables can be related very strongly. Sometimes the relationship is real, but it's a weak relationship. So bigger, stronger effect sizes or stronger relationships between our variables are going to give us more statistical power. They're going to give us a higher likelihood of rejecting the null hypothesis. Smaller effect sizes or weaker relationships that exist between our variables are going to give us lower statistical power. And this is the catch, because before we conduct our statistical tests, we generally have no idea what the effect size is between the variables. Otherwise, we wouldn't have to do the statistical test in the first place. And so effect size is this factor that influences statistical power that unfortunately we can't know before we actually run a test, right? The third factor that matters when in determining our statistical power is our alpha value, right? So bigger values of alpha will actually give us higher statistical power. Lower values of alpha will actually give us lower statistical power. This can be a little bit confusing, but think of it this way. I'm going to give you extreme examples. If we set our alpha value really high, let's say we set our alpha value to 0.9, right? That would mean that if we have a 90% chance that our null hypothesis is true, we're still going to reject the null hypothesis in favor of the alternative hypothesis. Or if we go even higher than that, let's say that we set our alpha value at 1, right? That means that no matter what, we are always going to reject the null hypothesis, no matter what our statistics tell us. So that's going to be a mistake a lot of times. That's actually going to lead us to make a lot of errors. But it's also, if we reject the null hypothesis every single time that we conduct a statistical test, we will always reject the null hypothesis when we should. We'll also always reject the null hypothesis when we shouldn't. But statistical power doesn't care at all about rejecting the null hypothesis when we shouldn't. It just wants to know how likely you're going to be to reject the null hypothesis when it's false, when you should reject it. And so if we reject the null hypothesis every single time, we are always going to reject it when we should. So that's going to actually be really high statistical power, even though it's going to lead us to make a lot of bad decisions, right? Conversely, if our alpha value is really low, that means we're making it really hard for ourselves to reject the null hypothesis. We'll almost never reject it, which means we'll very rarely reject it even when we should. That will give us very low statistical power, right? So that's why alpha matters in terms of statistical power. So this is just something to know, just to be informed. Researchers typically strive to achieve at least 80% power, right? They want to reject the null hypothesis when they should reject it about 80% of the time. But you really can only estimate your statistical power after you've conducted a test, after you can estimate the effect size, and you can really only then estimate your power for another test of the same hypothesis based on the sample size and the alpha value. And it's a really complicated thing to do, but just keep in mind, I want you to know what power is. We're never going to have to calculate it because it's a really hard thing to calculate, right? I just want you to understand what power actually is and what it tells us. So let's picture this, right? Think of power and alpha and the types of errors that you can make in this more visual way. So think about it this way. There's two things that can be real about the world in terms of our hypothesis. the two choices are our null hypothesis can really be true, or our null hypothesis can really be false. Those are the two options we have for what's really true about a hypothesis test, or about our hypothesis, specifically the null hypothesis. And when we conduct a statistical test, our data can tell us to do one of two things. It can lead us to fail to reject the null hypothesis, or it can lead us to reject the null hypothesis, right? So we have two things that could really be true, and we have two decisions that we could possibly make in our statistical tests, right? If we fail to reject the null hypothesis when the null hypothesis is true, that's a correct decision. If we are assuming the null is true, and it really is true, and we fail to reject the null hypothesis, then we stick with that assumption, and we've made a correct decision. If the null hypothesis is really true, but we reject it, that's an incorrect decision. We've made a type 1 error. Right? So a type 1 error is when we reject the null hypothesis when the null hypothesis really is true. The probability that that's going to happen is our alpha value. Right? So whatever we set our alpha value is, it's the probability that we're going to reject the null hypothesis when it really is true. If we fail to reject the null hypothesis when the null hypothesis really is false, that's another type of error. That's a type 2 error. And it has the probability of beta. Beta is, so power is 1 minus beta. Beta is the probability of failing to reject the null hypothesis when the null hypothesis is false, right? Again, this is something that we can't calculate, but that's why we use the term beta, right? If we reject the null hypothesis when the null hypothesis is false, that's the other type of correct decision that we can make. The probability of making this correct decision is the power of the study, or 1 minus beta, right? So we have two types of errors, a type 1 error, which has a probability of alpha, and a type 2 error, which has a probability of beta. And then we have two types of correct decisions. We can fail to reject the null hypothesis when the null hypothesis is really true, or we could reject the null hypothesis when the null hypothesis is false. And the probability of making that second type of decision is the power of the study. All right, so I said we can have two different types of hypotheses, directional and non-directional hypotheses. A directional hypothesis, we'll also call that a one-tailed hypothesis. An example of that would be, as hunger increases, patience will decrease, right? So the hungrier someone gets, the less patience they're going to have. The reason that this is a directional hypothesis is because we're making a specific prediction about what direction hunger is going and what is going to happen to patience, or what the patience variable will be doing as hunger changes in a specific way, right? We're specifically talking about hunger increasing and patience decreasing. So we're making a prediction about the direction of this relationship. Another example is students who attend class regularly will perform better on exams compared to students who do not attend classes regularly. So again, this is a hypothesis. The first variable is a nominal variable. It's got two categories, the students who attend class regularly and students who don't attend class regularly. And we're assuming that the students who attend class regularly are going to perform better on their exams compared to students who don't. So because we're making a specific prediction about which one of these categories is going to have the higher exam score, the better performance, that's a directional hypothesis, because we're making a prediction about which category is going to be bigger than which other category, or perform better than which other category. If I wanted to give non-directional examples of these tests, we could say that hunger and patience will be related, right? So I'm predicting that there's going to be a relationship between these variables, but I'm not saying anything about what the direction of that relationship is going to be. I would be correct, my hypothesis would be supported in this example if patience was higher as hunger increased, or if patience was lower as hunger increased, right? Because I'm not making a specific prediction about the direction of the relationship, either of those findings would support this hypothesis. Similarly, if we talk about our second example, if we say that test scores will differ between students who attend class regularly and students who do not, we are making a prediction about a relationship between the same two variables that we did as above, but because we're not predicting which group is going to be bigger than which other group, because we're only predicting that there's going to be a difference between the two groups, then the hypothesis is supported regardless of which group does better on the test. As long as there is a difference, the hypothesis is supported. We call directional hypotheses one-tailed and non-directional hypotheses two-tailed because we are going to go back to using that normal distribution in order to figure out the probabilities of support for these hypotheses. And we're going to get to that in a later lesson. But just for now, the only thing I want you to know is that directional is also called one-tailed and non-directional is also called two-tailed. And you'll start to see why as we start to test hypotheses. Okay? So that's been a lot. Let's summarize a little bit here. So when we conduct inferential statistics, which is what we're going to be doing for the rest of the semester, these types of statistical tests allow us to use samples of data to test hypotheses about a population. Our hypotheses in all the different statistical tests that we're running are always going to be about the population. We know, we can be sure, we can be 100% confident about the relationships that exist within our sample, right? Because we've measured everybody in the sample and we know how variables relate to each other within our sample. The big question is, the important question is, do those relationships tell us something meaningful about how the larger population that sample came from behaves, or whether those variables are related in the larger population? So our hypotheses are always about the population, and our statistical tests always tell us about the probability that the null hypothesis is true in the population, not within our sample. We use the sample to draw conclusions about the population. Right? So hypotheses are always, always, always about the population, not the sample. We always start by assuming that the null hypothesis is true. And in research, we gather data to test this null hypothesis or to draw conclusions about the null hypothesis. Because we're not measuring the entire population, the best that our statistics can ever tell us is the probability that the null hypothesis about the population is true. Right? We can never be 100% certain about whether or not our statistics tell us something meaningful about the population. The best we can do is be really, really sure. Right? And so always keep that in mind, that we won't ever say that our statistical test proved something about the population, because all we can do is have a high degree of confidence, but we can never be 100% sure. When we conduct statistical tests, we're going to set an alpha level. That alpha level is our criteria for when we're going to decide to reject the null hypothesis in favor of the alternative hypothesis. And finally, statistical power is the probability that we're going to reject the null hypothesis when the null hypothesis is not true. And we generally want that to happen. We make a prediction because we think there's a relationship between variables. So if our null hypothesis is that the relationship does not exist, we hope that we reject that null hypothesis in favor of the alternative hypothesis, that the relationship is actually true, that it exists, right? But we are only testing the null hypothesis, and the decision we make from our statistical tests is only about whether or not we reject the null hypothesis. We say we reject it or we fail to reject it. That's the best we can do. Okay? So that was a lot to digest for today. I suggest that you read over the chapters in the books that talk about this as well. And if you need to, go back and watch the video again. We're going to talk about this a little bit at the beginning of every single type of statistical test we do. So you're going to hear about this over and over again. But this lesson is the basis for everything that we're going to talk about for the remainder of the semester. So if there are things that you don't understand, you need to ask questions, you need to come see me in office hours, you need to watch the video again, you need to read the book again, but you need to make sure that you understand it or you're going to get lost, and I don't want that to happen. For next week, we're going to start learning our first statistical test. These are going to be the one sample Z test and the one sample T test. Definitely read these chapters in your book before Tuesday's class as well. Come into class ready to ask questions, ready to understand how hypothesis testing works. And if there are things that you're not sure of, you need to speak up, because we're going to start moving forward. And if you haven't gotten, if the basics on hypothesis testing and probability haven't sunk in, it's going to be really, really hard to keep up as we continue to move forward. Okay? Thanks, enjoy, have a great week, and we'll see you next week.